Seems to be working. Yeah, so again, we said this was positive because the other one, the field goes to the right, so you have to have something going to the left. Then calculating the charge of Q2, the positive charge, all I said was that the sum of the electric fields is 0 because they told me that right there. The net electric field is 0. So then I just do all that. To say what I'm doing there, I move this over to this side. Then once they're set equal, I cancel K's, and I get Q plus is this. And then I went up here to solve for 48. So I'm going to clear all that and continue. Calculate the magnitude of the electric force on Q2 and indicate its direction. So the electric force on Q2. If we're talking about the electric force on Q2, what is the only other electric thing? Q1. So, and since this is minus and this is plus, there's got to be an attraction that way. So the electric force is going to be K Q1 Q2 over R squared. That's all I do. So it's kind of trivial. 9 times 10 to the 9th. Q1 was negative 3 nanocoulombs. Q2 was 48 nanocoulombs. Remember, these are absolute values, so the sign goes away. And R is, what, 0.3 meters? 0.3 meters squared. Yeah, so there you go. I don't know, whatever that comes out to be. This is to the minus 9. That's to the 9, so that's going to give me 27. 0.3 squared is 0.09, right? So I can cancel out from the 27. That gives me 3 times 48 over 0.03. Wait, no, I'm sorry, just kidding, 0.01. So that's 3 times 48. 3 times 48 is 144. So it's like 14,400 newtons or something like that. I don't know. That's off the top of my head, so check it with your calculator. 9 times 10 to the 9 times this. That becomes 27.09. 9 goes away. It becomes 3 times that. 0.01. 01 moves the decimal place over. So I get 3 times 4,800. Yeah. Is that right? Anyone? No? Is that right? Okay, cool. So that's right, I think. So I think we're good there. Magnitude of the electric force. Okay, so we clear again. Determine the x-coordinate of the point on the line between the two charges with the electrical potential is 0. So we want to know between these 2 points, the spot where the V is 0. And remember, V is K times the sum of Q over R, right? That's what V is. And we want that to be 0. So we're going to say V is equal to K Q1 over R1 plus K Q2 over R2. Right? We want that to be, and then we're looking for that to be 0. The electric potential is 0. So once again, we get this same thing. K Q1 over R1 is equal to negative K Q2 over R2. K's cancel, and we're stuck. What do we do? Because we have two variables. Do those 2 variables relate in any way? Because we need another equation. How does R1 and R2 relate? Remember, this is like R1, and this is R2. How do they relate? They add up to be what, Preston? There you go. So we have our second equation. R1 plus R2 equals 0.3 meters. Okay, so Preston's given us the second equation, which allows us to solve this. So you can say whatever, I don't know. R2 is equal to R, whatever, 0.3 minus R1, or whatever you want to do. So then that means negative Q2 over 0.3 minus R1. And now you can solve it out. Because if I go up here, I'm going to get, if I cross multiply to make life easy on myself, Q1 is negative, well, it doesn't, yeah, Q1 is negative negative 3 nanocoulombs. So I'm going to get negative 3 nanocoulombs times 0.3 minus R1 equals negative, because we have a negative over here, 48 nanocoulombs times R1. So we can just get rid of that if you want. And then, yeah, just, I don't know, do the math however you want to do it. What, I guess you could divide both by the, no, that's the easiest way. I guess you just got to multiply it out. So this becomes 0.9 nanocoulombs minus 3 nanocoulombs R1 is equal to 48 nanocoulombs R1. And so then you get 0.9 nanocoulombs equals 51 nanocoulombs times R1. And so R1, ooh, that's weird. R1 becomes 0.9 over 0.51. Oh, sorry, not 0.51, just 51. And I don't know what that becomes. Some really tiny number. Because 1 divided by 50 would be, what, 0.02? No. Yeah, 1/5 is 0.2, so 1 over 50 would be 0.02. So this is going to be like 0.016 or something, 7, I'm guessing. What does it come out to be? 0.0176. So then it's like whatever. 0.0176. Oh, okay. That's from this, right? Now let's see. Determine the x-coordinate of the point. So be careful. This is R1. So what do I have to subtract here? Do you see? Do you see what I'm saying? This distance is from Q1. So 0.0176 from Q1, which is, whoa, that's really tiny. Yeah, it's like really close to that point. Yeah, so it's going to be negative 0.9824 or something. It's really close. And that makes sense, right? Because this one is 16 times bigger than that one. Okay, and then for D, oh no, sorry, we did D. For E, how much work must be done by an external force to bring an electron from infinity to the point at which the electric potential is 0? Explain your reasoning. Electron from infinity. So basically, you just calculate what is the potential energy of the electron and those 2 points. Yeah. So you have, if you put an electron here, then how much potential energy does it have between both of those 2 charges? And then And well, I want to go faster. All right, and then that's going to be the amount of energy it requires. So what I want to do to make things speed up is I'm going to show you the actual solutions guide. And I sincerely hope that I was right on my other ones, otherwise that's going to be embarrassing. Okay, so clear that, go here. And what problem is this? 3, question 1. Question 3, all right. So for question 3, we got our positive check there. That was 2 points. For 2B, I think we got 48 nanocoulombs, which is the same as 4.8 times 10 to the minus 8 coulombs, same smell, right? For 3, what do we come up with? 1440 newtons. It was a unit of issue of units. You know what I think I did? I forgot to put the nanocoulombs on here. Do you see what I mean? The magnet, like the numbers, right? It's just there was a second nanocoulombs on the 48. So if you took 14,400 and multiply it, don't do that in newtons, do that in nanonewtons, and then it works out. You get the right answer. Okay, so we're okay. I just forgot to put in the second nanocoulombs. So this, your answer, just make sure you put a nano in front of the newtons, and you're good. And this is on there. It's on the video as well, so you'll be able to see it. Okay. For part D, did we just do part D? Okay, well, let's see. That doesn't look promising. That looks like a different number. So let's see what they did. Okay, so we said this, and it's KQ over R. We said that. And we said KQ over D, 0.3 minus D. Okay, so everything looks good. So it must have been just a math error that we did here. Then what they did was it looks like they cross-multiplied and moved to the other side. So here they took this term, moved it to the other side, canceled out the K's, and just for some people who are freaking out, is everybody here okay with the fact that that's K? All right, K is equal to 1 over 4 pi E0. So don't freak out. They canceled these K's, they moved this to the other side, and then they cross-multiply. So they did all that stuff in one shot, and they get this, and then they get this. So I'm guessing I did something wrong with my mental math or some sort of thing like that, and that's why they got a different answer than us. Oh, you know what? I don't think they did get a different answer than us. Why is that number different from our number? Yet both numbers are correct. What's that? Yeah, they went from Q2. We went from Q1, right? So we were like 0.0176, right, meters from this, like this way. They are 0.282 meters from that. See what happens when you add those two together? You get 0.3. So we're good. Because I think, okay, maybe the last part. What do we get as our final answer? Oh my gosh, I subtracted, did I subtract 0.9? 9. Oh, that should have been 8. See, there's mental math. See it? It can't be, the answer, I think I said 0.09, but it can't be 0.09, because then that makes it more than 0.1, get it? So it's just a mental math error. Our answer should have been 0.0824, not 0.0924. And then that matches with their answer right there. Or I think we said negative, I believe, right? So we're good. We're good with that respect. So far, so good. No catastrophes. And then the network. Oh, yeah, okay. So then what we can say is the amount of energy to take any point to a point that has an electric potential of 0 is 0. And that's because work is Q delta V. But if delta V is 0, then work is 0. So there you go. So the potential energy is just the amount of work that is stored at that point, the amount of work that it takes to move it to that point. Alrighty. So that's that problem. Done.